Okay, today I would like to first of all finish the visitor pattern. I think the visitor pattern might be the most complicated one throughout the course. Okay, because somehow it builds on top of the composite pattern, and then the way visitor pattern works is not very intuitive. Okay, but I'll try to explain, using some simple example. But now let's just see what we have got from last time. From last time, we actually concluded with this diagram over here. We said that if you try to use the composite design pattern to model the structure of some small expression language, like for example, 2 plus 341, things like that. So you got expression there at the top, and then you got constant, we got addition, and then also got composite. So that's a composite pattern. Nothing wrong with that. But now the thing is, somehow we remember the open-close principle. The open-close principle tells us that there will be a certain part in your system that is open. There will be a certain part that is closed. The open part in this case is we got various of operations we would like to support on the language. In this case, we got evaluates, we got pretty print, we got type check, also we got generate C code, for example. So these operations over here which we want to support, or any further operations, they are not really related to each other. In this case, we are really trying to group unrelated things together in a single class. So that violates the principle for having a class. So what's the very definition for a class? That means we want to group relevant things together. If you try to group unrelated things together in a single class, that's not good. That's why we said this is not a good design. But what do we want to do? We want to learn the visitor pattern. The visitor pattern has the following advantage. Somehow we're going to say, let me just give you some intuition here, and I'm going to show you the architecture. Okay. Let's see over here. Let's see this diagram here. We got evaluates, we got pretty print, we got type check, we got generates. You can see somehow these 4 features, they are unrelated, but they are grouped into the same class. The intuition is very simple. We'll simply put them into separate classes, which means evaluates is going to be a separate class. Pretty print is going to be a separate class. Type check is going to be a separate class. Generate is also going to be a separate class, right? But they all share something together, which means they are going to traverse on the same tree structure like an expression, right? Even though they are different classes, okay? So that means later on we're going to group these classes together into another cluster, okay? That's kind of the intuition for visitor. We want to factor out all the language-specific operations into classes, into another separate cluster. Okay, let's see how we can do it. Now, this is the architecture for visitor pattern. Okay, let's go over the details first, and then we have to see how it works, and then I'll take questions. Okay, let's see this. I hope this is not too small, right? You can also download the diagram from the website. I also made it available. You can also look at that. Okay, I'm going to make some annotations on the board. Okay. So now let's first of all see how many clusters do we have. We got 2 clusters. Okay. First of all, we got this cluster here. It's called expression language. So this cluster here is the closed part for your system. Okay. I'm going to annotate that. So this is the closed part, which means this part here should be subject to no changes. If you have to make changes into this part here, visitor pattern is going to suffer, as we'll see at the end. Okay? And then the second cluster we have is called expression operation. Okay, that's another cluster. And this is the open part. Open part. You can see open and close. That's the open-close principle. You can always try to decompose your classes into separate parts, open and closed. Now the open part means it would be okay for the visitor pattern. Visitor pattern wouldn't suffer if we just keep adding new operation into the same language. You'll be okay. You can keep adding descendant classes over here. Okay, I'll get to there in just a moment. So we've got 2 clusters over here. And now let's see what we have known already. First of all, we still have a class called expression over here. And the expression still has the constant as the base case. Also, we have the addition as the recursive case, right? We're doing the composite pattern. Also, we got composite. That's something we have known already, okay? Now, let's see what's really new. What's really new here is something here. I'll highlight that. at the expression level here, we don't have any more like before. Evaluate, pretty print, type check, and generate. We don't have them anymore. Somehow they have been moved to the operation cluster. They have been moved. But now what do we have at the expression level? We have only one single feature, which is called accept. I'm going to write it out as well over here. Okay? I'm going to write it down over here. It's called accept. Accept. And then it's like a command. It's like a mutator. Accept and then v of type visitor. Now you might be wondering what is visitor over here. Visitor is exactly the root class in another cluster. Okay, we'll talk about the detail for visitor in just a moment. But now you should know that because of polymorphism, when we say accept at the runtime, what can be the dynamic type for this particular v? It can be any of the descendant classes, right? It can be, for example, evaluator, it can be pretty printer, or it can be type checker. Okay, just get it through first. So that's the, so over here you can see that feature there is deferred. Okay, you can see that's deferred. Deferred means we don't have any implementation at the superclass level. Now, for the constant and addition over here, we do have definitions. You can see that's why we got plus over here. We got plus over here, which means somehow we have to define them. Okay, let's see how we can define them. Okay, so now let's say this. I'll give you one example here. So you have constant over here. Let's say under constant, we have to implement the accept feature. Okay, we have v of type visitor. Okay, I'm gonna compare two versions with, for you. And then we also got accept. Let me just do it more properly. And then we also got addition. Okay, cannot spell properly. Okay, addition class, and then we also got the accept. But now we want to see how they are implemented differently. Okay, let's see how the implementation will go. Now, let's see the constant first. You will see that the way you implement the accept feature is very similar. First of all, let me write it out. You say do, and then n over here. Also do, and then n over here. Now, let's see what we can do. You simply say v dot visit constant. And then, what's the correspondence in IFO for this in Java? Current, thank you. Put current here. Okay, I'll explain what that means in just a moment, but let's see, okay? Now, it's really good to compare side by side. And over here, for the accept under addition, we say v dot. Now, you should realize that now we should have something that's different. If every accept feature in the descendant classes share the same implementation, then we would have defined them in the superclass, right? But now, if they are defined separately, then it should be different. Now, you want to take a guess? What should this be? Take a guess. It should be something different. For the constant case, we have visit constant. What about for addition? Visit addition. Wow, that's intuitive, right? Yeah, visit addition. Visit addition, and also you pass the current. Okay, so far not too bad. So let me highlight the things you should really pay attention to. First of all, we are under the context of constant. We have visit constant. When we are under addition, we say visit addition. Okay, and then over here, you can see we always call v over here and v over here the visitor. And now we always pass current, So what does that mean? That means whenever we want to evaluate for a particular, let's say this. Let me just put a tree over here. Let's say plus 3 plus 4. For example, a very simple expression over here, 3 plus 4. Overall, it's a multiplication, overall it's addition. Okay, let's say this particular expression here, let me call it add. So that's an object name, just add. Okay. Now, I can do different stuff for this particular add expression. I can try to evaluate it. I can try to pre-print it, I can try to type check it, or I can try to generate code from it. So now, how can I express to say I want to do different operation over here? Basically, I'm going to say add over here dot accept a particular visitor over here. Depending on what's the dynamic type of the visitor, is going to determine what kind of operation I'm going to perform on this particular tree. Okay, for example, if I give you you can see that the static type is simply just visitor over here. That means at the runtime, it can be any dynamic type. That's the descendant class. Now, if I want to do pretty printing, I can simply just create an instance of pretty printer, which is a descendant class of visitor, and then pass that to here. If I want to do maybe type checking, I can simply create an instance of type checker, which is also a descendant class of visitor, and then pass that object into here as well. So depending on what the dynamic type is, it's going to determine what operation is going to apply at the runtime. Okay? Any questions until now? I'm only talking about the left half. Haven't talked about the right half yet. Okay? And now maybe the most tricky part is, what do I really mean by current over here, right? So you're saying that when I'm calling a feature, I'm also passing myself to the feature, right? Basically, that's what it means. You realize this is actually quite important, okay? I'll show you in just a moment, okay? Okay, the green part is only the left half, okay? Let me just draw some over here. So now let's talk about the right half, okay? Let's talk about the visitor. First of all, you can see there's another package over there. Oh, you can see that over here. There is a client-supplier relationship over here, right? You can see from expression is a client of visitor, simply because it declares a feature accept, which has declared the type visitor. That's why we got client-supplier, which means expression is a client of visitor. So visitor is a supplier. But what kind of supplier is this? Supplier over here can be a evaluator, it can be a type checker, it can also be a pretty printer, right? Can be different kinds because we got an inheritance hierarchy over here, okay? Now, let's see how the right-hand side will work. Let's see that, okay? Let's try to see what's really defined at the upper level, okay? How about I just add another picture over here in the next page. This one's getting a little bit messy, okay? The page below. Let me just add another image over here. Photo, camera. The one I want is possibly this one here, right? Good. Okay, now let's talk about the right half, okay? Let's get it clean. Now, again, at the top level, we got something called visitor, under which, now one thing to note, can you just tell me what you see? We got evaluator over here, we got pretty printer over here, we got type checker over here. These are classes. Go back to the original design. We got evaluates, we got pretty print, we got generates, we got type check. Do you see the difference? Somehow in the design pattern for visitor, we convert each operation from feature into classes. So that's a key, right? Because we say that each operation we want to perform on a language has nothing to do with each other. Pretty print is very different from type checking. Type checking is very different from generating the code. So that's why they should not belong to the same class. So they should be separated out. And the way we do that in a visitor pattern is they should belong to a separate class alone in isolation. Okay, that's what happened in the visitor pattern. Okay, now let's see what features we have to support in the upper level. Okay, over here I'm going to repeat. Over here we have two features. The reason that we have two features is simply because we only have two descendant classes over here in the expression. You can think about the way we define a visitor, which is a supplier, the way we define what feature they should have corresponds to what elements we have in the language structure from the client side, depending on what we need. Okay, so I'm going to write it out. We have something called, so under visitor, which is the ancestor class, so we got two features. Visit constant In this case, we have C of type constant. And we also have something called visit addition. And over here, we have A of type addition. Okay? We only have two features. Okay? Let me just make a note for you. So these two here corresponds to the list of descendants. How about I say effective descendants? Effective means they are not deferred. They are simply the concrete ones. The concrete ones are simply constant addition of descendants of expression. Okay, to make it even more explicit for you, you can see that you got constant here, you got addition here, right? Okay. Now we want to see how we implement these. Okay, let's see how we do that. Now, let's see this. First of all, we got something called evaluator, we got pretty printer, we also got type checker. What about we try something called evaluator? Why don't we try that first? Okay. How about pretty printer? Pretty printer is actually easier. Let's try the easier one first, and then I'll show you on the slide for evaluator. So now let's try pretty printer. Pretty printer. Okay. Under that, we got visit constant over here. And then we simply got C of type constant. Okay? Now, if you are inside the context of pretty printer, that means the particular operation you would like to do at the moment is pretty printing. Now, how do I know what kind of pretty printing I'm going to do? Should I be a pretty printing on addition? Or should I be a pretty printing on constant? It depends, right? So now for this particular feature here, visit constant, that means I'm currently visiting a constant. So now, how should I do in terms of pretty printing? I can simply print out the constant's value, right? So now, what I can do over here is I can simply say, you can say do io dot print. And then I can say c dot, if you look at the design over here, you can see that we actually assume the constant actually has a value itself. Okay, let's assume that's the case, okay? Okay, c dot value. Okay, any quick question before I show you also how you can define visit addition? That one might be more interesting to see, okay? Okay, so this is visit constant. Again, the one we are looking at is really constant. Let's try another one. Okay, I'm gonna put it here. Let's say we got visit addition. And then we can say A of type addition. Okay, now, how do we define this? You can see that this feature over here, which is called visit addition, it's under the same class called pretty printer, which means when we are taking this particular input addition, what we want to do with it is we want to do some pretty printing, right? Just like before, when we take constant, we want to pretty print constant. Now we want to pretty print this addition. Can you imagine how you do pretty printing addition? But the left may not necessarily be a constant, right? Since we talk about composite. The addition itself, the left might, well, let me just make it. For example, you might have something like this. Plus, you also got plus over here. And then you got 2 and 3, you got 4 and 5, right? That's another possibility, right? So now, yeah, so somehow you can see the left. Now let's just go back to the composite pattern here, just to make sure. You can see that the left and the right, what's their type? Their type was not just constant, right? Their type was expression, which means that you can arbitrarily build out the tree as complicated as you like, right? So it can be also addition, right? Of course, the tree I drew before was only a simple illustration, right? It can be as complicated as this or even more complicated, okay? Hopefully you see the point. Now, when we say I want to visit the addition for pre-printing purpose. Let me just annotate. This might be good to say. So now you can say that, so now you visit the constant over here for pre-printing. And over here, also you visit the addition for pre-printing. Okay, so now, any suggestion? How do we do it? We want to somehow also pre-print the left and the right, right? How do we pre-print the left and the right? Rob? You're getting there. Somehow you want to recursively do something. Because I want to visit the addition, I simply have no idea how complicated the left or the right is. So I can say recursively visit and recursively visit. Yeah, do some.
Across addition, across C, print.
Across C over here, right? I see what you're trying to say. You're trying to across every child and then try to pre-print every one of them. But now the thing is, for this particular design, remember we got only left and right because that's kind of special expression, right? So now, I see what you're trying to say, but I'll try to correct that and then show you. You can see that we only get left and right. Why don't you try to revise your answer using only left and right? How would you express your answer only use left and right? What would you do for left? How would you pre-print the left? Let's make it even more specific. There is no such thing called pre-print in this context. How would you pre-print the left? That's a key. You want to somehow recursively handle the left subtree, and then recursively handle the right subtree, and then do something in the middle. Okay, that's basically what you want to do. Anyone? You can think about it. You know, that's really the key, right?
Should it be visit expression because it could be either constant or addition on the left-hand side?
No. That's the beauty of a visit design. So over here, you see the visit addition over here, we say that the parameter type is addition. That means we're currently visiting addition. Of course, the left and right, they can be arbitrarily complicated, but there's a way to do it. Guys, how about I give you a hint? I don't want to give you the answer right away. It's really important to think this through. The hint is, look at actually the diagram here is cleaner. Look at this side over here. Look at this side. Now, if I say I want to pre-print the left, I also want to pre-print the right, what should I do? Yeah, go ahead. Yeah, the left-hand side is an expression, right-hand side is also an expression. But now, how do you say I want to pre-print the left and also pre-print the right? How do I do it? There's no pre-print function per se that's defined. We only get accept, we only get visit addition and visit feature. Accept left. Okay. You're getting there, but you're saying the opposite order. Okay? Let's try. Okay? Do you want to say something before I give out a solution?
Print the left and then recursive across the right.
When you say print the left, again, how would you print the left? You wouldn't say I would print and then the left. That wouldn't work. Right? Okay, let's try. So this is what you should do. Okay, let's write it out and then let's discuss that. What you can do is, first of all, you know that we can say A dot left. What's the type of this? No, A dot left. Not A. Oh, you see, A is of type addition, right? Expression. Very good. You can see expression over here. Now, A dot left is expression. What can we call? Accept. Dot accept. Accept what? You can see accept over here. So do some back to your concern. If we want to pre-print the left, we want to make sure we are consistently applying the same operation throughout. So we want to really apply the same operation as the current. The current is the pre-printer, right? MJ? Yes, that's exactly what I'm doing here. But you can see, you're going to pass something over here because accept takes a visitor. Huh? Next level? Yeah, exactly. When we say A.left, we are really going to the next level. So what you really put is current. The accept, the current. Okay? And then also we can say io.print sum plus. And then can you guess what the next step is? We should accept another one, right? You should really say a dot write dot accept. And also you have current over here. Okay, I just went out of space. So now look at the thing I'm going to highlight. You actually call accept over here. You also call accept over here, right? Any question about how we define these two visit features here? And then maybe we should really see how things work together. Maybe we should see that. Okay. Let's go over some slides, and then I will show you one simple run. Okay. But I think in principle, what we have done in the visitor pattern is you can see all the operations are grouped into the same cluster. Right? Go ahead. Thinking this way. Now let me just draw some conceptual picture. How about this? Okay, let's say this. So let's say, let me just enlarge the context for you. Let's say now we are under, when we say class, and then let's say pretty printer. Pretty printer. Under which we have visit constant. And then it takes some addition over here. And there's something we do over here, okay? Now think about what's happening here. A is some reference to some addition, right? Some addition, which has some left subtree, which can be arbitrarily complicated. It can be constant, or it can be another addition, right? And also it has right subtree. The way we go about this is to say, if you want to visit the constant, and now the visit constant here has a special meaning because we are now under the context of pretty printing. That means whenever you say you visit a particular node in this context, you're trying to pretty print, okay? Now, how do we go about that? What we do is you would say that to handle the left subtree, we simply say a.left, which is an expression. And then we want to recursively actually handle that. And we just delegate the job again to say a.left dot accept. And now, what should we pass as the argument for the accept? We want to make sure, since we are doing pretty printing, we cannot simply just pass we got to pass another pretty printer, right? Rather than passing a type checker. In that case, that means overall you're doing pretty printing, but for the left-hand side, you're doing type checking, right? That's not consistent, okay? That's why you'll simply just put current over here. And then you also have a.write dot accept. And over there, you say current. Okay, that's what you have. And then you somehow combine the result together. The way we combine them is to say, this part over here is going to print out something, followed by printing out the plus sign, and then followed by the printing out of the right-hand side. That's how we handle the pretty printer. Okay. Now let's imagine this. Let's using the same tree. Let's just bring another context, class into context. Let's say we talk about a class, another descendant class. If you look at the diagram over here, let's talk about evaluator. Okay, let's talk about it. Yes, question first. Visit addition. Thank you. Thank you. That's definitely a typo. Thank you. Thank you. Good. Now, let's talk about another class which is highly relevant. Let's talk about its sibling. So now we used to talk about pretty printer. Now let's talk about evaluator. So class evaluator. Now what do we do? Now let's talk about the same feature over here. So the list of features you have over here should correspond to the descendants of expression. So we also got visit, visit constant, and also visit addition. Okay, let's talk about visit addition. And then here, let's say A, also addition. Over here. And now, what should we do over here? Okay, conceptually, it's easy because now, rather than pretty printing, now this visit addition here has a special meaning because the context is different. It's now an evaluator. Now, how do we do about that? We should somehow evaluate the left-hand side, the left subtree, and get its value as an integer, and then evaluate the right-hand side, the right subtree, also as an integer, and then add them up together. That's what we should do. But now, how do we go about that? Okay, now, I will also show you the slide in a moment, but why don't we do it now? Okay, so now let me just erase this. I'm going to make some space for myself. The way to do about this is we can use some attributes and local variables. I'll show you how you can do it. Okay, and you will see in the slide it's exactly the same. Now, let's think about this. You're free to add additional features or attributes in your individual visitor as you need. Let's say for the evaluator, one very intuitive way to do it is to say, once I evaluate this particular component of the expression, I want to store the result as an attribute, right? So next time when anybody want to query about what was your evaluation result, they can say the visitor dot value, right? Let me give you an idea. Let's say in the evaluator class over here, I declare an attribute. I can say value over here, and then it's simply just integer. So that's something unique to the evaluator, unique, which means every time if I say evaluate on the left-hand side, it's going to give me the left-hand side value. If I say evaluate the right-hand side, it's going to give me the right-hand side value. Okay. Now, what about local variable? I can say, let me just make it intuitive to you. I can freely declare more than one visitors to help me. I want to say, to evaluate the left subtree, let's use a separate evaluator. To evaluate the right subtree, let's use yet another evaluator. Okay? And then query about their values individually, add them up together. Okay? How do we do that? What I can do is I can say left over here, let's say left eval, and of type evaluator. And also right eval, that's of type evaluator. Okay, I'm just declaring two extra variables. So the left eval is going to be responsible for visiting the left subtree, and the right eval is going to be responsible for visiting the right subtree. Okay, now how do we do that? So now this is what I can say. I can say that, first of all, we can say A over here is addition. A dot left is going to be of type expression. And the expression is guaranteed to have the accept feature available. So I can say A dot left dot accept. Okay, any suggestion over here? What should I put? I heard current. Current is not too bad, but if you use current here, it can be a little bit confusing. I will let you figure out how to make current work appropriately since we got some auxiliary variables over there, right? Any suggestion? Left eval, exactly. Very good. Why don't we put left eval, right? Let's put left eval over here. Any more suggestion? What should I do something similar? I should do A dot right over here, and then dot accept. Now here, be careful. If I pass left eval again, what's going to be disastrous is I'm going to override the result for the left subtree. Right? That's why I declare another extra variable. I can say right eval. Okay? Now, haven't done yet. Yeah, just let me finish this and I'll take your questions. Now, what should I do? I haven't really got a result for overall. So what I should do is I should say now value for this current evaluator, which is responsible for the addition. Okay? Value is assigned to left eval dot value plus right eval dot value. Okay, this is really the key. Okay, I will highlight it. Okay, and then you should really realize that over here, the value over here really corresponds to this value over here. Okay, that's what we're doing. Okay. Well, I'm only showing you the supplier code. I haven't really shown you how you can use the visitor, but we'll see that. Yes.
Well, we're in the
Visitor cluster. Mm-hmm.
which is the
Supplier of the expression.
right, and the evaluator in the visitor function cluster class, the evaluator class, which is effective has a visit constant
Yes.
and
Also visit addition.
visit addition. Right, so it visits, but it doesn't accept.
You visit, yes, but inside the definition for the visit, we can accept. You see what I mean? Okay, how about this? Yeah, how about this? Let me just do one more illustration here. Yeah, I do see where your confusion might come from. Okay, let me just do one more. Let me try it from a different perspective. Let's try this. Let me do the following. Let's say we got let's say add 1. Okay, that's the node. Add 1 and add 2. And then we have constant number 1. Let's say in this case, it's simply just 3, the value. And then here we got constant number 2, which is, we got constant number 2, which is a value 4. And then constant number 3 of the value, let me give you a different value, 6. Overall, we should get 3 plus 4 plus 6, which is 13 overall, right? Let's see how things work. Okay, let's see that. Let's say we start with this. The client only knows about the reference to add number 1, the top level. Okay? If we say the following, if we say, let me use a different color here. If I say add 1 dot accept, okay, something over here. Let's say we want to do evaluation, okay? Now, let me just make some decoration over here. Let's say eval over here of type evaluator. And don't forget, evaluator is a descendant class over here, right? Of visitor, okay? Now, I say accept eval. Let's see how this is going to work, okay? Now, how is this going to work? Let's review very quickly the definition for accept for addition, right? You can see the dynamic type of add 1 is simply just addition. So it is going to call the accept that's defined in addition. Okay, let's have a quick look, which I already talked about. You can see that the accept in addition over here has the visitor dot visit addition, right? That's what you have. Okay, let's see how that's going to be reflected on the tree over here. So that means what we have is this. We're going to have eval dot visit what? What do we have? You know what? I didn't draw the tree very appropriately. Let me just do it again. I shouldn't really branch out. Let me just, okay? Now, let me do it again. When I'm calling this line over here, so what does it do? It's going to execute this block of code for visit addition over here. Okay, now, what do we have? We have eval dot visit something. What do we visit? Here is critical. Since add 1 over here is of type addition, right? And now if you go back to the original code, that's why current over there was really important. Over there you can see that when you are in visit addition over here, when you say visit, it's going to say accept current, right? That's what you would say, okay? So what you would say is, hey, everybody follow? Okay. Accept, and then it would say visit addition over here. Sorry, I went to the wrong page. Okay, over here. Okay. Now what we'll do is we'll say v dot visit addition. And this guy here is the current at 1. Any question about this step here, or you guys are confused?
Confused is because in the slide it says for the evaluator class it says a.left.visit eval left, and you wrote
On the accept, right?
sorry.
Okay, why don't we go over the slides now? Maybe that was further confusion. I kind of forget what I put on the slides, okay? Why don't we go over a slide very quickly, okay?
Slide 9.
Okay, I'll come back to here in just a moment, but actually over here, it's about the open-close principle we just talked about, right? So here, the language structure is closed, and the operations is open, okay? Now, let's just go over here, okay? Now, let's talk about the cluster expression language. I'll come back to this example in just a moment, okay? I'll come back there, okay? First of all, we have the accept feature that's defined in the expression class. And then we have to make sure for every descendant for the expression, we define the accept, okay? So now, for accept, in the context of constant, we're gonna say visit constant and then current. That's what I said on the iPad. And then we say, inside the context of addition, we're gonna have the accept and then visit addition and then current, okay? Okay for now, the same as before, just showing you on the slides. Now, let's move to the visitor cluster and see what happened. Now, for the visitor cluster, we want to make sure for every descendant class in the expression, we have something specific to that particular class. So we got visit, addition, and visit constant, right? That's what we have. Now, at the third level, at the top level, under visitor, we got visit constant, and also we have visit addition, okay? As said before. Now, what about evaluator over here? For evaluator over here, so what we have is, we can define some value over here, right? So that's going to store the result for the last evaluation, okay? So here we can have visit constants. Visit constant is actually quite easy. How do you visit a constant? Constant, it basically is already the base case. In that case, you don't have to do any further visiting, so it's already terminating case. In that case, you can simply say the value is simply c.value, and value is simply an attribute for the constant class, right? Now, what about visit addition over here? Now, somehow we have to recurse on the left and on the right, but how do we do that? So as I said before, the way we do that is we simply have eval left and eval right, and they're both evaluator. And then we can say a.left dot, that should be accept. You see what I mean? Yeah, that's your confusion. Yeah, so that's a typo, okay? Yeah, you know, over here, guys, you see this typo, right? A.left is of what type? Expression. So what do we have available in the expression? Only accept. Sorry, that should be accept, not visit. I know it's confusing, that should be accept, okay? So a.left, so what I said on the iPad was actually right, okay? So maybe when I was typing, I didn't double check. So a.left dot accept left, and also a.right dot accept as well, okay? And then we can add up their values. Now hopefully that makes more sense. Guys, are you okay with the code so far? I haven't done the tracing yet, but I think we should do that. We should complete that, okay? Why don't we complete the example? I'll fix the typo after class, okay? Okay, let's go back to the iPad and then let's try again. So now, when we have, let's try to really make things work for you. So now, what about this? Let me go back to the code over here. First of all, you can see that at the top level we say add1.accept. So let's review the definition for accept. What's the definition? Definition for accept would be simply just v.visit addition and then pass the current. And what's the current? Current is simply the context object add1. So that's why we say eval, which is the evaluator, dot visit addition, and then the context object, which is add1. Okay, that's the first level. Okay. Now, what next? Now we have to look at the code for visit addition. So now a question for you. Which version of the visit addition should I look at? Which version? We actually got, how many versions of visit addition do we have? If you look at the architecture diagram over here, how many versions? Visit addition. 4? 3, right? 3, because we, at the top level here, this is deferred. That's not even a version. It's just a decoration over there. Version number 1, visit addition for evaluation. Version number 2, the visit addition for pretty printing. Version number 3, the visit addition for type checking. So now, which version should we go to? Which version? Why would we go to the version of evaluation though? Because? No? Well, do some? Why? Okay, so now when we say eval.visit addition here, right? We talk about dynamic binding. For dynamic binding, depending on which the dynamic type is, for eval over here, we're going to call the corresponding version. Right? Guys, are you follow? Okay? If you don't follow, you're going to speak up. Otherwise, I'll assume you're okay. Okay? Okay? No? Yes, please. Okay, I can repeat, definitely. That's a valid request, right? Okay. Okay, first of all, are you okay with the first line, first of all? We say, oh, sorry, not this one. When we say add1.accept eval, you're okay with that one, right? So add1, basically, this is the pointer to some objects of a type addition, okay? So now we know that. Let me just make some annotation for you. For add1 over here, you can see that the dynamic type is addition. Okay, good. Now, and then we say accept over here. Now, when we pass eval over here, what's the dynamic type of eval? So somehow we are trying to, well, of course I didn't put it here. You can say creates evaluator eval dot make. In this case, we know that the dynamic type is evaluator. Okay, follow so far? Now, let's see this. When we want to see what happens when we make this feature call, we have to make sure we know which version this is calling, right? So now let's look at the first line. How many versions of accept do we have? How many versions? Let me go back there. How many versions of accept? 2. Very good. Which 2? In constant and also in addition. Now we want to know which version it is going to call. Tell me one. Tell me which version. Is it going to be the version in constant or the version in addition? Addition, right? Because that dynamic type is addition. So we're going to call that version there. So we go to the version for, let me just go back there. So we go to the version for visit accept over here in addition. So over this version over here, right? And then it's going to call v.visit addition, right? It's going to call that, okay? Now, something I want to mention here, when you go from, let me just use a different color here. When you go from here to here, this is something called the first patch. Okay, I'll explain what that means. Dynamic type of add1 is addition. So this implies which version we're going to call. So version of accept in addition. is called. Okay. Can you follow this line here? Okay, good. Now, if we go to the version of the accept in the addition, what is it going to do? It's going to say, whatever visitor you're passing, v.visit addition, and then pass the current addition, right? The current one, okay? So that's why you got this second line over here. And that's exactly over here. Eval.visit addition at 1. Okay? So basically this is what you see over there as the current. And this is what you see over there as the V, the visitor. We're going to swap the order. Okay? Guys, are you lost? Were you okay? Which part? You're going to tell me which part you're lost. I know visitor pattern is not that easy. Okay, you got to tell me which part. Yeah. Uh-huh. The left part and the right part here. Mm-hmm. Actually, depending, okay, that's important. You see, when we go from this line here into the second line over here, how do we know that we're going to call visit addition rather than visit constant? How do we know that? It's simply because the dynamic type of add one is actually addition. That's why we go there, right? And then, now, when we get to this line over here, how should we continue? In this case, which visit addition are we going to call? Which version? You know, the version here is really important because if you look, again, that's why the visitor pattern can be complicated because over here you can see that, let me just go back to the diagram. Okay, this is where I want to go. If you look at the diagram here, for expression over here, you got more than one descendant classes, which means at the runtime, you got more than one possible dynamic types. And for visitor over here, also at the runtime, you can also have more than one possible dynamic types. Okay, that's why it's actually complicated. So when you first to say some expression.accept, depending on what the dynamic type is, you're going to go to that particular descendant class. And then that descendant class is going to say visit something. Let's say, for example, let's say if I'm inside the context of addition, I'm going to say visit addition. But now for the visit addition, which version am I going to? I got visit addition over here. I got visit addition over here. I also got visit addition over here. Now it depends on which visitor I pass to it. If that was the evaluator, so you can see now we actually go back and forth, right? First we start from here, and now we traverse, go to this package over here. And then if the visitor we pass, for example, was evaluator, in this case, its dynamic type is evaluator. Now in this case, that guarantees we're going to call visit addition in the evaluator over here. Okay? Okay, maybe that kind of answer your questions? Yeah.
That answers a lot of it, but I was wondering, so you know, we do the dynamic binding for visitor.
Yes.
So if we go down to whatever visitor issue.
Mm-hmm.
Why don't we also do dynamic binding for expression?
We do actually, we do. Because you can see that over here, actually we already do it in the first step. When I say add one that accept some visitor, I'm already doing dynamic binding because depending on what's the dynamic type for this particular expression over here, I'm actually going to do it. How about this? How about do one more? Do you see it? Yeah? Okay, now the diagram is a bit polluted, so let me just do one more because I cannot. So guys, if you're really confused, maybe watch the video, okay? Let me mention one more. Because what's really important, okay, the number one thing to understand about visitor pattern at the runtime is something called double dispatch. Okay, let me just mention that again. Double dispatch. Okay, you can also see the slides. Let me just do one more example, okay? A simple one. Let's say I have add over here. Let's say add, and then I have constant number 1, which is 3, and constant number 2, which is 4. Let's say I have that. Okay, that's a small example. Let me try again to explain. When I say add, oh, actually, let me just also put evaluator. Now, over here, I say add expression. And then I say creates create addition, and then you can say add dot make. You can see the dynamic type is really addition, right? Okay, just showing you some code. Now, let's do visitor very quickly. And I also have eval, which is of type evaluator. Let's say I want to do evaluation. Okay, now I can say creates over here. And then, you know what? Let me just do something like this. Let me do one more. Let's say V over here, visitor. And then I say eval over here, evaluator. Oh, sorry. Let me do that properly. I would say creates evaluator, and then v dot make. Okay, now you can see what the dynamic types are. For expression, it's addition. For visitor, it's actually evaluator, right? So these are the two dynamic types that's going to determine how the runtime behavior is going to, to be executed. Okay, let's try this. When I say add dot accept, and then I say v over here. Let's see how this is going to work, okay? Let's say very clearly from this simple example. We know that for add over here, dynamic type is actually addition. Okay, first of all. So now this is the first patch. Whenever I say patch, a single patch simply means depending on what the dynamic type is, we're going to call the corresponding feature. Okay, so now first patch. Call the version of accept in addition. Okay, let's see what it will do. For that one, for accept in addition, you simply say v.visit addition and then current, right? Okay, what you will do is something like this. You can see, thank you. You will simply say something like this. You will say v.visit addition. And then we say current, which is add, right? Now, again, we have another situation for dynamic binding, second patch. Let's now analyze the dynamic type for V over here. Okay, you can see what's the dynamic type for V? Evaluator, good. If you put evaluator over here, so that means the version of visit addition we're going to call is going to be evaluator because we got 3 versions there, right? We're going to call that particular version. So now this is second patch. Call the version of visit addition in evaluator. Okay, so now what would this do? Okay, let's now look at the definition there. Let's go back to slides and then you will see that. Okay, you will see that the visit addition in evaluator is you will simply just evaluate the left, evaluate the right, right? That's what you will do. Okay, so over here you will simply do something like let me just use a different color here. Okay. And over here, we'll simply say add dot left dot accept. Oh, thank you. You know, I keep forgetting. Keep forgetting. Thank you. You know, at least I know you guys still care, right? That's good. Yeah. I'll be very upset if I do this for 10 minutes and then nobody care, right? Okay, accept. And then we'll have eval, left eval. Okay, that's the left-hand side. And the right-hand side will be add dot right. And then right eval. Sorry for the messy writing, but do you actually see how double dispatch over here works? Let me just summarize what double dispatch works. Starting from the top, we are trying to evaluate certain expression. The way we evaluate that is by passing the right dynamic type of visitor. We say add, which is some composite expression there, add the accept v. The dynamic type of v is actually evaluator. That means eventually we're going to do evaluation only. We're not going to do any type checking or pretty printing, okay? So the dynamic type in the visitor pattern is really important. Now, the first patch is going to decide which version of the accept is going to be called. In this case, because the add has the dynamic type addition, so we're going to call that. And why calling the right version is really important. You can see the green one over there is going to call visit addition rather than visit constant, right? And when you go to the green part over here, we're going to have the second dispatch. Because now, v.visit addition, we want to know which visit addition we are calling. Right? Now, how many versions do we have? Depending on how many visitor descendants you have. In this case, the dynamic type of v is actually evaluator. That means we're going to evaluate the add using evaluator. Right? So that's why we're going to call that version there as the second dispatch. And then we're going to do further according to the definition. Guys, any questions about this before I show you more sample code? But I think that in terms of tracing the program, this is something you should really have clearly in your mind, okay? Double dispatch. Typically, in the object-oriented programming like a Java or C#, they only support single dispatch. But this is how we simulate double dispatch. Okay, you could do two things. Okay. First, expression, and then visitor. Okay. Let me show you more sample code, and then hopefully we can finish that. So now, let's see how this can be done. Okay? Let's see how we can run a test. Let's say we got add C1 and C2, and we got some visitor. Okay? And now we say that create some constant with value 1, create some constant with value 2. And then we say create addition with C1 and C2, which is C1 and C2, they are the children of the addition. And then we got evaluator. You can see the red part are the dynamic types. They're going to determine how the operations are going to be performed. Now, when I say add the accept, it's going to call the accept version that's in addition. And then it's going to call the version of visit addition in evaluator. Okay, the two dispatches. Okay, that's something you really want to review the slides and review. Now, let's see how we can use it. After this, we can be confident that after visiting add recursively by using v, now we can query about the result to say, what's v? V is simply some evaluator, and then we can say eval.value, which is 3, which will be 1 plus 2. Okay? Now, if you go over the slides, that tells you double dispatch, and then it's basically just what I said on the pad. Okay? Guys, any questions before I make some conclusion about visitor pattern? You know what? It's a very good question. How about this? I promise I will either create a tutorial video for this or I will demonstrate in class, okay, to show you how the double dispatch work. Okay, I'll do that. Okay, guys, any more questions about this before I just make some conclusion? Now, for every design pattern, you have to know when to use it and when not to use it. For visitor pattern, you should also know where to. Maybe it is applicable to your projects, maybe it is not. Right? You want to make sure you know how to judge. Okay, let's see this. Let's see, just give you some guidance. Now, let's see. Let me just, first of all, let's go back to the architecture. Okay. Now, okay, we have gone through this already. Okay, let me just do one more architecture diagram over here. Let me just add it, and then I'll ask you. It's really important to know. So now we have this guy here. Oh, actually, not this page. A new page up below. And then add image. Oops. Okay, good, very good. Now, let's talk about the extension, okay? Now, what are the possible extensions to this pattern over here? What are the possible extensions we can do to this extensions? There are two kinds of extension you might do. Either you can say add a new expression. For example, let's say I want to support subtraction, for example. That's the first kind. What about the second kind of extension? Let's say I want to add a new operation. Let's say I want to have add a new visitor. Right? Basically, either expression or visitor. You can just do either one, right? Now we're going to discuss which extension is easy for visitor pattern, which extension is hard. Add a new visitor, for example. Let's say I simply say simplifier. Okay, I can just going to simplify the expression. Okay, now, which one do you think is easy to do for the visitor pattern? Yes. Which one is easy to do? Easy. And why?
Visitor pattern is to add a new visitor.
So you're talking. So Dusan, what you're trying to say is adding a new visitor is easy.
Yes.
How?
To do so, in the visitor root node, we just add a new feature called
Not a new feature, a new class. You meant
like business.
new class, right? So let's say this,
Yeah, you have
right?
class
Mm-hmm.
simplifier,
Mm-hmm.
and honestly, implement two features that the visitor class.
Okay, exactly. So what you would do is you're going to do simplifier, and then you simply in a single place you actually implement visit constant and visit addition in a single place. So single choice principle is obeyed. It seems to be easy. Add a single class, and then in that single place you implement all the feature that's deferred. What about adding a new expression? What's going to happen here? Anybody want to try? Somehow this is going to violate the single choice principle. Before I point to anyone, think about it why. Look at this, it's really important actually because it's really important for you to see which extension is more possible for your problem. If it is more possible to add a new visitor, you should choose visitor pattern. If it is more possible to add a new expression throughout the development of your project, in that case you shouldn't choose visitor. Okay? Guys, think about it. What does it really mean if I want to add a new descendant class to expression? Let's call that subtraction. What does it really mean? What do I need to change, right? Okay, somebody want to raise their hand? And yes, go ahead, please.
So first of all, you just have to inherit the expression and also on this side.
Okay, let me do step by step. Okay, first step, I need to have a subclass over here called subtraction. And over here, I can just do a set over here, right? Okay, second step. Yes, I agree. Yes, that's good. I like that. Yes. Which feature? What feature are you talking about? Visit subtraction, which means I get to first of all add this one over here. Visit Subtraction. Subtraction over here. And what's the consequence of that? Exactly. In that, so because every child has to implement this particular feature over here, in that case, are we obeying the single choice principle? We are. No, we are not. You gotta wake up. Okay. Yeah, no, we are not. Okay. Actually got interrupted. Okay. Anyway, no, we are not. Because in this case, if we add a visit subtraction in the visitor class over there, that means every descendant class will be forced to implement a particular visit subtraction feature, right? So that's not obeying the single choice principle, it's violating that. Which one? Yes, you know, at the visitor level, yes, the visit subtraction should be deferred. But since it's deferred, every concrete descendant class must implement that. Otherwise, they have to be deferred as well. It's a bit like in Java, abstract class means you got at least one method that's not implemented. If you have some concrete class that is not abstract, that implements some abstract class, you got to implement every abstract feature, abstract method. Now, since we're introducing something that's abstract, you got to make sure it's implemented, right? No, that wouldn't work. Okay, questions, please. Yes. No, it wouldn't work. Because if you only have visit expression there, well, I tell you what, in some way that was not too bad. Okay, the question was, what about we simply got something here called visit expression over here? And then here we simply got E and then expression, right? That's what you're saying, right? Think about how you're going to implement that. In the descendant class, let's say for pretty printing, how would you know the dynamic type for this one? You have to somehow use some if then else check, right? Oh, you're saying the following. Okay, I see what you mean. You say visit expression over here, and then you will simply say no, you wouldn't do it because I tell you why. Okay, it's a very good question. Let me just handle this one. And then let me handle this one at last, and then we are done. Okay. Okay. I think you can read it through. So this kind of tells you which one violates, which one does not violate. Okay. You can read it through, and then we are done. Let me just handle this question last, and then we are done. Okay. The question was, what about the following design? Let me handle that. Okay. Let me just add that image again. Photos. Okay, we got 5 minutes actually. We got more than enough time. Okay, but let's handle this. The question was, what if at the top level over here, why don't we simply do something like this? Visit expression. E expression. That was a great question, okay? Why not, right? Okay, yeah, well, wait, hold on. Now, if this is deferred at the visitor level, that means we have to implement that for every descendant class, right? Let's take evaluator, for example, okay? Let's say now we are in evaluator, okay, evaluator context, and then we have visit expression. E expression. Okay, and then, so this is what we got to figure out. Okay, think about this. Dynamic binding wouldn't actually work so well for us in this case. Why? Because when I say E, the static type is simply just expression over here, right? But now, I have to do some discrimination over here. Because if E happens to be a constant, I don't have to visit anymore, any further. If E happens to be some addition, in that case, I got to do E dot left, E dot right. And you know what? What's even the trouble? If I say, for example, E dot left expression over here, would this even compile? Guys, back to your lab test number 2. Would E dot left compile? Okay, I can see you knocked your head, okay? Why not? Because expression is a static type. Does expression define left? No, because that only belongs to the composite, right? So now that's why you're going to separate them out. If you really want to have a single visit expression over here, what you're going to do is as follows. If E instance of, I'm just using Java term, if E is some dynamic type is actually addition, they're going to cast that into some variable and then do the left and right. You're going to repeat this pattern here for every visitor class. In that case, your code will smell. Okay? Okay, let me just mention something here, and then I think we got a little bit more. Okay, guys, any more question about visitor before I close this topic? Yes, go ahead. Yeah. Yeah, they're separate. So let me just repeat. The question was open close principle versus single choice principle. They're different. Single choice principle simply means every time you want to make a change to your system, there should be a single place where you make the change. If there's going to be multiple places, then that violates the single choice principle. Okay? Now, open close principle simply means for your system, you can always separate that into 2 parts. One is the open part, where you mean that part you can always change. You can actually use open for extension. And there's also some closed part. Let's say in the case of the visitor pattern we are talking about, the closed part is simply the structure of the language. Because when you try to add a descending clause to expression, you're going to violate the single choice principle. Right?
I still thinking like it should violate the single choice principle because if you add a feature in visitor, visit, subtraction, then you also need to implement it in all the descending.
But there's a single class. There's a single class you're adding you're implementing all the features. When we say one is actually just the absolute value 1. It's conceptually just one place you're adding, you're implementing all the new operations. Okay. Okay, guys, any more questions?
For example, some design principle might violate some other design principles. Like sometimes they.
Well, I wouldn't say that's true in general. So those design principles should be able to be satisfied at the same time. So for your projects, okay, let me stop the recording and then I'll give you some comments.